6 minutes ago, somewhere in the Chilean mountains, a machine the size of a small car finished taking another picture of the sky. And with that single image, it just added to a body of evidence so strange that scientists are still struggling to explain all of it. Because what this machine has already found in less than a year of existence is not a discovery. It is a flood of them. A river of stars twice the width of our entire galaxy. An asteroid spinning so fast it should not physically exist. A star that may have died without an explosion. And a visitor from another solar system that nobody even knew had passed by until they went back and checked the footage. This is the story of the Vera Rubin Observatory. And if you have not heard what it just did, you are about to understand why astronomers are calling this the most disruptive machine ever pointed at the night sky. Snorts. Let's start with the moment that changed everything. On June 30th, 2026, after 25 years of construction, testing, delays, and quiet anticipation, the Vera Rubin Observatory officially switched on its real mission. Not a test, not a preview. The actual 10-year countdown began. It is called the Legacy Survey of Space and Time in Warp. And here is what that actually means in plain language. Every 3 to 4 nights, this observatory photographs the entire visible southern sky. Not one galaxy, not one star, the entire sky. Then it compares that new image to the last one it took. If a single dot of light has moved, brightened, dimmed, appeared, or vanished, the system flags it instantly. Scientists at SLAC National Accelerator Laboratory confirmed that once the survey reached full operating speed, it began generating around 7 million alerts a night. 7 million. Every single night. That is not an image. That is a live nervous system wired directly into the universe. To understand how big of a leap this is, you need to go back 1 year to June 23rd, 2025, the day the world first saw what this telescope could do. That day, using only about 10 hours of test observations spread across just 7 nights, Rubin released a single composite image of the Virgo cluster. Inside that one image were approximately 10 million galaxies, not stars, galaxies. Each one potentially containing billions of stars and countless unseen worlds. And according to NSF and Neil Lab, that jaw-dropping number was only about 0.05%, 1/20th of 1%, of what Rubin is expected to capture across its full 10-year survey. If 10 million galaxies felt overwhelming, sit with this for a second. Rubin is aiming to eventually observe roughly 20 billion galaxies. We have barely opened the door, and the room is already too big to see the walls. But numbers alone do not explain why so many scientists are unsettled and thrilled at the same time. It is what was hiding inside that first data that changed the tone in observatories around the world. Buried in the earliest images, astronomers spotted something nobody had cataloged before. A stellar stream stretching an estimated 163,000 light-years, torn away from the spiral galaxy Messier 61. That distance is longer than the diameter of our entire Milky Way. A structure that size, sitting quietly in the sky, and no survey before Rubin had the width, the depth, or the patience to notice it. That is not a small detail. That is proof that huge galaxy-scale events have been happening around us the whole time, and we simply did not have the right eyes to catch them. Here's the part that should genuinely make you pause. Every telescope before this one operated the way a photographer works. Point, focus, capture, done. One subject, one shot, one moment frozen in time forever. Hubble gave us incredible detail. James Webb gave us the ancient infrared universe. But neither of them was built to repeatedly return to the same patch of sky again and again, comparing what is there now to what was there before. Rubin was built entirely around that idea. Scientists have started describing it in a very specific way. Rubin does not just photograph the universe. It gives the sky a memory. And a universe with memory behaves very differently than a universe frozen in a photograph. It starts confessing its secrets. A missing star becomes a clue. A shifting dot becomes an asteroid. A faint smudge becomes a 163,000 light-year river of stolen stars. So, if the first 10 hours of test data already produced 10 million galaxies, a hidden galactic stream, and enough asteroids to make headlines, the obvious question is this. What happens once the machine is running at full power for a full year? What happens at year 5? What happens at year 10? Before we go there, I want you to understand exactly how strange some of these early objects actually are, because one asteroid in particular is currently breaking laws of physics that scientists thought they understood. Stay with me, because in the next section, we are going deep into the object called 2025 MN45, a rock twice the height of the Empire State Building that is spinning so fast it should be tearing itself apart in real time, and nobody can fully explain why it isn't. Let's talk about the asteroid that should not exist the way it does. Its name is 2025 MN45, and on paper, it sounds like just another rock floating in the asteroid belt between Mars and Jupiter. But once astronomers actually studied its behavior, it turned into one of the strangest objects cataloged in recent memory. According to a peer-reviewed study published in the Astrophysical Journal Letters on January 7, 2026, this asteroid measures about 710 meters across. That is nearly twice the height of the Empire State Building, floating in space, tumbling through the dark. And here is the detail that made scientists stop scrolling and start double-checking their data. This asteroid completes a full rotation once every 1.88 minutes. Less than 2 minutes for something the size of a skyscraper to spin completely around. To understand why that number is so alarming, you have to understand what most asteroids of that size are actually made of. Researchers led by astronomer Sarah Greenstreet at NOR Lab and the University of Washington explained that most asteroids in this size range are what scientists call rubble piles, loose collections of rock and dust held together by nothing more than weak gravity, like a pile of gravel barely clinging together in space. A rubble pile spinning that fast should not survive. Centrifugal force should rip it apart, scattering debris across the solar system. But 2025 MN45 is still there, fully intact, still spinning at a speed that scientists openly admitted they did not expect to find in an object this large. Co-author Dmitry Vavilov of the University of Washington said plainly that for asteroids around 700 meters wide, nobody expected to find one spinning faster than 10 minutes, let alone one spinning nearly 5 times faster than that. So what is holding it together? The leading theory is almost as wild as the discovery itself. Greenstreet and her team believe 2025 MN45 may be a fragment blasted off the dense, superheated core of a much larger planetary body that existed early in our solar system's history, a body that was later destroyed in a violent ancient collision. If that theory holds, this asteroid is not just a rock. It is a surviving piece of a planet that used to exist, spinning through space for roughly 4.5 billion years. And we only just now noticed it. 2025 MN45 was not traveling alone. That same research identified 19 newly confirmed fast rotators in total, all of them larger than a football field. 16 were classified as super fast, completing a rotation somewhere between 13 minutes and 2.2 hours. 3 were classified as ultra fast, spinning in under 5 minutes, with 2025 MN45 sitting at the extreme edge of that group alongside 2 others, 2025 MJ71 and 2025 41 Malawian Quachas. What makes this even more remarkable is the timeline. This entire data set came from just 7 nights of observation collected back in April and May of 2025 during Rubin's very early commissioning phase, months before the telescope had even been switched into its real 10-year mission. This was a warm-up, a stretch test, and it already broke a record that had stood unchallenged for the entire history of asteroid science. Zoom out, and the scale becomes almost impossible to process. During Rubin's pre-survey optimization phase in early 2026, in a window of roughly 6 weeks, the observatory identified more than 11,000 previously unknown asteroids, including 33 near-Earth objects and 380 objects orbiting far beyond Neptune. 11,000 new asteroids in 6 weeks, before the real survey had even formally begun. Now, here is the number that should genuinely stop you. Scientists at Rubin Observatory and Near Lab project that in its first full year of operation, the telescope could discover around 1 million previously unknown asteroids. 1 million. For comparison, that is roughly equal to every asteroid humanity has painstakingly cataloged over the previous 200 years combined. 2 centuries of work potentially doubled in 12 months. Why should any of this matter to you if you are not an astronomer? Because asteroids are not just floating debris. They are historical records. Each one carries physical evidence of how our solar system formed, how planets collided, migrated, and settled into the orbits we know today. Sarah Greenstreet herself pointed out that finding asteroids locked into specific motion patterns, particularly ones synchronized with Neptune's orbit, could help researchers finally trace how the outer planets drifted to their current positions billions of years ago. And there is a more immediate reason to care, too. Scientists are hopeful that Rubin will dramatically improve our ability to detect small, meter-wide asteroids just before they enter Earth's atmosphere, what researchers call imminent impactors. Current simulations suggest Rubin could catch around one of these events per year, and instead of a few hours of warning, it could give scientists a couple of days of advance notice before a fireball lights up the sky. That is enough time to point instruments at the right patch of sky, deploy sensors, and actually watch the moment of impact unfold in real time, rather than analyzing it after the fact. So, we now have a telescope finding a rogue fragment of an ancient shattered planet, spinning nearly 5 times faster than physics comfortably allows, sitting inside a haul of 11,000 new asteroids discovered before its real mission even started. If this is what a warm-up phase produces, what happens when the same machine turns its attention towards something even stranger? Something that does not spin or orbit, but simply disappears. In the next section, we are going into the discovery that some astronomers are calling the most unsettling of all, a star in the Andromeda galaxy that may have died without ever exploding, and a silent visitor from another solar system that slipped past Earth for 10 days before anyone noticed. Now we get to the part of this story that genuinely unsettled astronomers, because this is not about something appearing in the sky. This is about something disappearing from it. Scientists call it a failed supernova, and it might be one of the strangest kinds of stellar death physics allows. Normally, when a massive star reaches the end of its life, it goes out in the most violent way imaginable, exploding outward with enough force to briefly outshine an entire galaxy. That is a supernova, and it is bright, dramatic, and impossible to miss. But a failed supernova does the opposite. Instead of exploding, the star simply collapses inward on itself and folds directly into a black hole. No blast, no flash, no warning. One moment, there is a massive star. The next moment, there is nothing where it used to be. For decades, this was only a theory, because catching a failed supernova is uniquely difficult. You're not looking for something bright. You're looking for an absence. A star that was there and now is not. In a universe filled with billions of stars that all look similar until one of them quietly stops existing. According to research published in the journal Science in February 2026, astronomers pinpointed a possible candidate for exactly this kind of event in the Andromeda galaxy, roughly 2.5 million light-years from Earth. Stephen Smart of the University of Oxford, who leads the science team behind one of Rubin's key data alert systems called LASER, said Rubin is uniquely positioned to catch more of these events because its images go about 100 times fainter than other sky surveys. In plain terms, Rubin can see the kind of quiet stellar death that every previous survey on Earth was simply too weak to notice. If that Andromeda candidate is confirmed, it becomes direct evidence that some of the universe's most massive stars are collapsing into black holes silently, with no announcement at all, which means there may be far more black holes scattered across the cosmos than anyone has ever counted. This is exactly the kind of discovery Rubin's alert system was designed to catch, and the scale of that system is almost hard to describe. On February 24, 2026, Rubin ran a live test of its alert pipeline by photographing a patch of sky that already had a strong historical baseline. In a single night, it generated 800,000 alerts. Every object that changed, appeared, or vanished was automatically flagged and cataloged. Stephen Smart described it simply. Everything that changed triggered an alert, and that was still just a test. Once the full legacy survey of space and time launched on June 30, 2026, the system stepped up to its real operating scale, an estimated 7 million alerts and roughly 20 terabytes of new data every single night. 7 data broker networks around the world, including LASER, now exist purely to help astronomers sort through that fire hose in real time. One of the biggest reasons this matters comes down to something called Type I supernova, a very specific kind of exploding star that astronomers use as a cosmic measuring stick. Back in the late 1990s, two research teams studied fewer than 100 of these supernovae and made one of the most important discoveries in modern physics: that the expansion of the universe is accelerating, driven by a still mysterious force we now call dark energy. Once Rubin's full survey is running at capacity, scientists expect to find around 250,000 type I supernovae every single year. Not 100, a quarter of a million annually. Researchers are hoping this flood of new data can finally help resolve the Hubble tension, a long-standing disagreement in physics where the modern universe appears to be expanding faster than early universe measurements predict it should. If Rubin's supernova data can settle that argument, it would resolve one of the biggest open questions in cosmology. But stars are not the only things slipping through the dark that Rubin is built to catch. It is also becoming one of the most powerful tools ever built for tracking visitors from outside our solar system entirely. In all of recorded history, astronomers had only confirmed a small handful of interstellar objects, asteroids or comets that originated around other stars and simply passed through our neighborhood before continuing on their way. One of the most recent was an interstellar comet called 3I/Atlas, first announced on July 1, 2025, after being detected by a separate network of telescopes called Atlas. Here's the part that genuinely surprised researchers. When astronomers went back and checked Rubin's own archive data afterward, they discovered that Rubin had already captured images of 3I/Atlas 10 full days before Atlas ever announced it. 10 days. The object had been sitting quietly in Rubin's data the entire time, and nobody had looked yet. Astrophysicist Rosemary Dorsey of the University of Helsinki said scientists genuinely do not know how many more of these interstellar visitors Rubin might catch once the full survey is underway, estimating it could be anywhere from 5 to 500, depending on how frequently these objects get ejected from other star systems in the first place. So, think about what that really means. A telescope that can retroactively notice a visitor from another star system 10 days after it already passed by unnoticed in real time. A star in a neighboring galaxy that may have died in complete silence. An alert system processing 7 million changes to the sky every night. More information than human astronomers can fully process in real time. This is not a telescope anymore. This is a live surveillance system for the entire visible universe. And yet, everything we have covered so far, the asteroids, the vanishing stars, the interstellar visitors, all of it is just the visible layer. Underneath all of it lies the real reason Rubin was built in the first place, and it has nothing to do with what we can see. In the final section, we're going into the invisible universe itself, the dark matter and dark energy that make up the vast majority of everything that exists, and why scientists believe this observatory may finally answer questions humanity has been chasing for over 90 years. Everything we have talked about so far, the galaxies, the asteroids, the vanishing stars, the visitors from other solar systems, all of it is the part of the universe we can actually see. But here is the number that should make you sit back in your chair. Everything visible in the cosmos, every star, every planet, every galaxy, every human being who has ever lived, makes up only a small fraction of what actually exists. The rest is made of dark matter and dark energy, two forces that dominate the universe and that scientists still cannot directly explain. And this is where the story of this observatory becomes personal, because it was built specifically to hunt for them, and it was named after the woman who first proved they were real. The observatory is named after Vera Rubin, an American astronomer whose work in the 1970s changed physics forever. Rubin studied the rotation of galaxies and noticed something that did not add up. Galaxies were spinning so fast that, based on the visible matter inside them, they should have been flying apart entirely. Something invisible had to be holding them together, providing gravity that no telescope could see. That invisible substance is what we now call dark matter. And Rubin's observations became some of the strongest evidence that it exists. She never lived to see this telescope carry her name into operation. But in a very real sense, this entire 10-year mission is the continuation of the question she first asked half a century ago. What is actually holding the universe together? Here is how the observatory plans to answer that question. As light travels across the expanding universe toward Earth, it stretches and shifts toward the red end of the spectrum, a phenomenon called redshift. The more stretched the light, the farther away its source. By measuring this shift across billions of galaxies, a technique called photometric redshift, Rubin can map how mass, including invisible mass, is distributed across unimaginable distances. Astronomer Kristen Dage of Curtin University confirmed that Rubin's early preview data already showed the technique performing at least as well as other leading telescopes. And once the full 10-year survey is complete, Rubin is expected to measure the redshift of roughly 4 billion galaxies out of the 20 billion it will ultimately observe. For billion galaxies mapped for distance and structure, effectively building a chart of where the invisible skeleton of the universe actually sits. And dark matter is only half of the invisible puzzle. The other half is dark energy, the mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow down. Scientists still do not know what dark energy actually is, where it comes from, or whether it will continue forever. But by tracking roughly 250,000 type Ia supernovae every year once the survey reaches full speed, Rubin is expected to give researchers one of the most detailed independent tests ever conducted of whether dark energy behaves as a fixed constant or whether it has been changing over the history of the universe. If it turns out dark energy is evolving rather than constant, that would be one of the most significant findings in the history of physics, forcing scientists to rewrite fundamental assumptions about how the universe will end. So, step back and look at the full picture one more time. In June 2025, this telescope opened its eye for the first time and immediately produced 10 million galaxies in a single image, along with a hidden 163,000 light-year river of stars that nobody had ever cataloged. Within months, it had identified more than 11,000 new asteroids, including one spinning almost 5 times faster than physics comfortably allows. By February 2026, it had flagged a candidate star in Andromeda that may have collapsed into a black hole without ever exploding, and confirmed it had silently photographed an interstellar visitor from another solar system 10 days before any other telescope on Earth even noticed it was there. And on June 30th, 2026, it switched on its true 10-year mission and began generating 7 million alerts about the changing sky every single night for the next decade. We spent thousands of years looking up at a sky that seemed permanent, fixed stars, frozen constellations, a universe so vast and so slow that a human lifetime felt too short to ever notice it move. Vera Rubin's observatory has already proven that this was never true. The sky was never still. We just never had a machine capable of remembering what it looked like yesterday, so it could catch what changed today. Now we do. And it is already finding failed stellar deaths, rogue asteroid fragments, hidden galactic rivers, and visitors from other stars in less than a year of partial operation. So, here's the real question, and I want you to actually sit with it before you go. This telescope has 10 years left to run. It has barely scratched the surface of what it is capable of finding. If the first few months alone produced discoveries this strange, what is waiting in year 5? What is waiting in year 10? How many hidden black holes have formed in total silence that we have never detected? How many interstellar visitors have already passed through our solar system without a single human being noticing? We are not just watching a telescope collect data anymore. We are watching the universe get caught in real time in the act of changing. If this kind of story pulls you in the way the universe keeps quietly rewriting what we thought we understood, make sure you are subscribed, because this observatory is going to keep making headlines for the next 10 years, and you do not want to miss what it finds next. Drop a comment below and tell me which discovery from this video shocked you the most: the spinning asteroid, the silent star in Andromeda, or the interstellar visitor that slipped past US for 10 days unnoticed. And if you want to go even deeper into how astronomers are racing to map the invisible universe, there's another video linked right now that you need to watch.